one important fact about continuous functions is the so-called intermediate value theorem. So the intermediate value theorem says that if a function is continuous on an interval from a to b, then for every value between f of a and f of b, there's an x value between a and b, so that f of c is z. So this is a mouthful, but it's actually saying something very intuitive about functions. So let's suppose, so here's the x-axis, and suppose that we have some function defined on the interval from a to b, and it's continuous. So that means it takes some value over at a, it takes some value over at b, and in between it's continuous. Now, suppose someone comes along and gives you a value, so sorry, here's f of a, and this height down here is f of b. Now suppose someone comes along and picks a number between f of a and f of b, in here somewhere. Let's call it z, and they ask you, is there an input on the x-axis that produces z as an output? Right? And that's the role that c is playing. C is an input that produces z as an output. Well, is there any way that we can connect our point up here at a and this point down here at b without running across this height z? Well, the only way to do it is, right, we could jump across the height z, but that's not allowed because the function is continuous. Another thing we could do is maybe have some sort of asymptote that lets us get past z, but that also violates this continuity condition. So continuous functions, they have to pass through, there has to be some input where the graph passes through the height z. And that's really what this intermediate value theorem is saying. You have to take on all intermediate values if your function is continuous. And actually, it's also important that this interval be closed. So it's sort of intuitive, but it lets you learn things about continuous functions without having to explicitly know where this value c is, right? This is a powerful theorem because it guarantees that this input c exists without having to tell you exactly where it is. And that's nice because finding exactly where it is might be essentially impossible. All right, let's look at an example of how we can use this intermediate value theorem. All right, let's show that this equation, sine of x equals 1/2 x, has at least one solution besides 0. X equals 0 is clearly a solution because sine of 0 is 0, and 1/2 times 0 is 0, so x equals 0 is a solution. But how could we be sure that there are any other solutions? Well, one thing we can do is, right, it doesn't at first look like this has anything to do with the intermediate value theorem because we don't have just one function. Right? The intermediate value theorem is talking about just a single function. But anytime you have an equation, you can make it a question about a single function just by moving everything to one side of the equation. So we can do that. We get sine x minus 1/2 x equals 0. So you can see this is now a question about whether this function, sine of x minus 1/2 x, has 0 as a value. Well, the intermediate value theorem says, first of all, this function is continuous continuous for all real numbers, right? Because it's a sum of functions that are continuous for all real numbers. So the intermediate value theorem says that if we have any two values that this function produces, it has to also produce all of the intermediate values. So let's see what sort of values this function produces. Let's find, say, f of pi over 6. So this is sine of pi over 6 minus 1/2 times pi over 6. Sine of pi over 6 is a half, so minus 1/2 pi over 6. So this is 1/2 minus pi over 12. Pi over 12, well, pi is about 3, so pi over 12 is about a quarter. So this is about a half minus a quarter, so it's about a quarter, but at any rate, it's positive, definitely positive. Okay, what about, say, pi? What about f of pi? Well, that would give us sine of pi minus 1/2 pi. Sine of pi is 0, so this would be minus 1/2 pi. So that's negative. So the situation now is that at pi over 6, this function is positive, and at pi, this function is negative. And this function is continuous. But the intermediate value theorem says there's some x value where this function takes on the intermediate value 0. So the intermediate value theorem says there is an x value c in the interval from pi over 6 to pi, so that f of c is 0. But remember, f of c, that's sine of c minus 1/2 c. And this means that sine of c equals 1/2 c. In other words, c is a solution to that equation. And also, since c is between pi over 6 and pi, c isn't 0. So we just guaranteed that there's at least one other solution to this equation that we were looking for. Notice that the intermediate value theorem doesn't really give us a very good idea of what this value of c is. It just says that it's somewhere between pi over 6 and pi. All right. We can actually extend this a little bit, because although the intermediate value theorem on its own doesn't give us a very good idea of what c is, we can actually repeatedly apply this intermediate value theorem idea to sort of narrow down where this value c might be. So for an application, let's see how we can repeatedly use the intermediate value theorem. So the setup here that we were just looking at was that we have this equation that we can't solve exactly because it's too hard for some reason. And the equation is 0 equals some function, right? So in our last example, this function was actually sine of x minus 1/2 x. Okay, and we had one input where the function was negative and another input where the function was positive. And also our function is continuous on the interval between those values. Then the intermediate value theorem guarantees us that there is some solution, but how can we find the solution more accurately? Indeed, to any desired accuracy, right? So the intermediate value theorem just tells us there's a solution somewhere between a and b, but it doesn't really tell us where. For another example of this kind of equation, look at this. So e to the x equals x plus 2. So it's pretty clear that there are solutions to this equation. Even a very rough graph, right? This is 1 right here. Even a rough sketch of a graph will show you that there must be solutions. Right, here's e to the x, and then x plus 2 looks like this. So it looks like there are going to be two solutions. But if you try to do algebra to solve this equation, you won't be able to solve this equation. It turns out having the variable in an exponent and also not in the exponent makes this equation basically unsolvable. So what we can do is rearrange this equation so it looks like this. E to the x minus x plus 2 equals 0. Now based on the graph, it looks like if we go from 0 over to, it's hard to know exactly where this spot is, but there's definitely going to be one solution between these two spots. So let's try x equals 0. So here our function now is e to the x minus x plus 2. So when we plug in 0, we get f of 0 is e to the 0 minus 2. So 1 minus 2, that's minus 1. Okay. So at 0, we know that this function is negative. So this is 0. All right, let's try x equals, how about 2? So f of 2 is e squared minus 2 plus 2. So this is e squared minus 4. But e is bigger than 2. So e squared is bigger than 2 squared. So that's 4. So e squared is bigger than 4. And so e squared minus 4 is bigger than 0. So this is larger than 0. So over here at 2, the function is positive. Now the intermediate value theorem then tells us that there must be a solution somewhere between 0 and 2. Of course, we don't know where it is. But what we could do is, let's plug in the midpoint here. How about 1? So let's calculate f of 1. That's e to the 1 minus 1 plus 2. So e minus 3. This is negative, right? E is about 2.7. So e minus 3 is definitely less than 0. So that means that this function at x equals 1, it's negative. Well now, right, so the intermediate value theorem no longer tells us anything about the interval between 0 and 1 because we're looking for a place where this function crosses the x-axis, but 0 is no longer, the height 0 is no longer an intermediate value because both of these are negative, right? 0 isn't between two negative numbers. So the intermediate value theorem doesn't tell us anything about the interval from 0 to 1 anymore, but the intermediate value theorem now tells us that this solution that we know exists, it must be between 1 and 2. We don't know where between 1 and 2, but somewhere. So to get more information, why don't we check 3/2, right? 1.5. So we can evaluate f of 3/2. So that's e to the 3/2 minus 3/2 plus 2. And here we have to start using a calculator, I think, because I don't know what e to the 3/2 is. So e to the 3/2 minus, let's see, 2 plus 1.5, so 3.5. Okay, I get, it's about 0.9. So positive. That means at 3/2, this function is positive. Well, now the intermediate value theorem doesn't tell us anything about the interval from 3/2 to 2, but it tells us that there is a solution between 1 and 3/2. So now we can plug in the midpoint here. So this is going to be, I guess, 1.25. So let's evaluate 1.25. So this is going to be e to the 1.25 minus 1.25 plus 2. Sorry, 1.25 plus 2. So e to the 1.25 minus 3.25, 3.25. This is 0.24. So positive again. So positive. So now the intermediate value theorem tells us that there's a solution between 1 and 1.125. Oh, sorry, 1 and 1.25. You can see every time we do this, what we're doing is we limit ourselves to the interval where the function switches from positive to negative. We take the midpoint of that interval and we check if the function is positive or negative on that interval. If it's positive, then use the interval on the left. If it's negative, use the other interval. And whichever one you get, positive or negative, we're always cutting the possible range, right? We know a 0 has to live in here somewhere, and at every step, we're cutting this interval where the 0 might live in half. So if we want to know where the solution to this equation is to any desired accuracy, all we have to do is keep repeating this process until we've cut this interval in half so many times that it's very, very small within the desired accuracy. So this way, this subdivision way of finding approximate solutions to equations, it only depends on both sides of your equation being continuous. and plugging in a bunch of values to get approximate function values. Of course, this is something that a computer can do very, very quickly, and in fact, this is how some numerical software packages solve equations approximately when they can't solve them exactly.